Thank you very much to the organizers. I'm very proud to be to give this concluding talk. I will talk about an algebra I developed for reasoning about non-deterministic computations. Non-deterministic algorithms are attributed to Robert W. Floyd, who wrote in 1967, non-deterministic algorithms resemble conventional algorithms, except that one may use a multiple-valued function choice. All points of terminations are labeled as successes or failures. He also quoted George Harrison, saying that all the time life is a fork. If you are straight up with yourself, you don't have to decide which road to take. Your karma will look after that. Are non-deterministic algorithms strictly more efficient than deterministic algorithms? In 1975, Ladner proved that if P is not equal to NP, then there are infinitely many complexity classes between them. All examples of such intermediate problems are very artificial.
Except for party games.
That one is an exception. A clean class of problems within NP was suggested by Fraser and Vardy in their seminal work. Their goal was to find a sufficiently large class of NP which exhibits a dichotomy. And they studied uniform constraint satisfaction problems. Constraint satisfaction problem is identified with the homomorphism problem. Given two relational structures, the question is there a homomorphism between them? The second structure is called a template, and non-uniform CSPs are those where the template is fixed. Fraser and Vardy conjectured a dichotomy. Non-uniform CSPs are either in P-time or NP complete. Bulatov and Zhuk closed that conjecture positively. They used the techniques of universal algebra. Our setting here in this talk are computational decision problems: three-colorability, ST-reachability, various counting problems, such as whether the input domain is even. We have queries, and the queries ask, is this graph three-colorable? Is the size of the input domain of the structure even? We look at data complexity. Query is fixed, and structures vary. The goal here is to develop an algebraic language for reasoning about non-deterministic computations in a deterministic way. In particular, for reasoning about the set of certificates of computational decision problems as a mathematical object, to study that object for symmetries. We will see a mechanism for constructing such an algebra. In particular, how to tame the non-determinism of classical connectives, how to use algebra as a logic, as a query language, how to quantify in this algebra over certificates algebraically, how to reason about the existence of a certificate, how to capture complexity classes with such an algebra. In my construction, I started from fixed point logic with least fixed point operator, well known from the work of Immermann and Vardy. I was inspired by good algorithmic properties by two variable fragments. I partitioned the variables of atomic symbols into inputs and outputs. I produced an algebra of functional binary relations on finite strings of structures over the same relational vocabulary. This is an algebra of binary relation. In such an algebra, we take a binary relation, and each operation produces a binary relation. Here, the binary relation is on strings. They are on strings of structures of a certain vocabulary, which is partitioned onto the extensional database vocabulary, which is the input vocabulary, such as the vocabulary of the graph, the edge relation, and registers. Registers are unary predicate symbols that are required to contain one element at a time. They're singleton sets. Let's look at this algebra. The main connectives are counterparts of classical connectives. Negation, conjunction, disjunction, iteration. A counterpart of reflexive transitive closure, or the Kleene star. There are equalities and atomic elements, which I will explain. They are a modification of unary conjunctive queries. There is also an identity. That will be explained back globally. Intuitively, the operations are as follows. The main fundamental property is that they are function preserving. That is, if atomic relations are functional, then so are all algebraic expressions. The operations are unary negation or anti-domain. It essentially says that there is no outgoing transition. Initially, it was introduced this way. This is the intuition behind unary negation. There is no way to extend from A to any C. Composition is a standard function composition. Preferential union. It is a counterpart of union. We perform T, and if not possible, we perform G. They are partial functions. So the first one may be undefined, and in that case, the second one is applied. There is a maximum iterate. Essentially, we take the Kleene star and output the longest transition out of all possible transitions. I have an illustration on the next slide. Back globally, here we use the predicate symbols that are registers. And in fact, we only access domain elements via comparison or when we perform atomic transitions. We never access them directly. Back globally, we check whether the content of the register P now is different from anything before in Q. Equality check simply compares the content of two registers now at the end of a string we are at. This is the intuition, and this diagram illustrates the difference between maximum iterate and the Kleene star. The Kleene star is not a function. From a structure, we can go to many other structures. And maximum iterate is a partial function. We always have only one way to proceed. I deal with it with restricting choice functions, which will be described shortly. Choice functions are fundamental to this approach. When we have conjunctive queries, such a query returns a set. It's a unary conjunctive query, it returns a set. A choice function picks one element out of that set. And that choice function is history dependent. It is formally described on the next slide. But if we look at an example, this is a conjunctive query. If we have an edge relation, there could be multiple transitions from x to y, multiple edges. And if x is reachable, then we put reachable star. In the reachable star, we put all such elements that are reachable. And there could be many such elements because there could be many edges from x. But we use a choice function to pick just one such element. And that defines a transition in a transition system. Instead of writing a conjunctive query first and then saying there is a choice operator, we use a different arrow instead of the traditional data log arrow. It means that only one element is put into the relation. Formally, choice functions are functions from atomic actions, essentially, that refer to conjunctive queries, to partial functions. Partial functions on strings of structures. A choice function returns a functional binary relation, but it can be also viewed as an atomic transduction. For example, if AB was from the transition system was selected, that's in the transition, then we have the choice function contains these two strings. V is any string, and from A we transition to B. That's how it looks. Then choice functions are extended to all terms, and perhaps the main thing, I will not go through the definition, but the main idea is that not all choice functions are extendable. For example, we may not be able to compose two atomic actions. And there are multiple choice functions like that. As a result, for each graph, we have something what I call a multi-structure. It's a graph where we have strings as the main elements, and then according to each choice function, we have multiple graphs. You can think of them as edge relations. Briefly about the origins of the constructs, the epsilon operator is due to Hilbert. Unary negation first appeared in the work of Gronendik, as far as I know. Maximum iterate and preferential union are from Jackson and Stokes. The algebra is equivalent to a linear time dynamic logic. It's much more convenient to work with the logic. And such a logic is produced via a standard embedding. You can think about the first line as process line and the second line as state formulas. And state formulas are unary in the same sense as P of x is a unary notation for P of xx. All of the formulas in the second line are subsets of identity and interpreted by subset of identity. What is a test action? A test action is negation applied twice. Anti-domain of anti-domain is domain. So this is a test. Any expression can be there. And the modality is perhaps the most important concept here. Inside the modality, we have a term which formalizes a program. And this is the same as the domain of the program followed by the property that holds after. We can define a satisfaction relation for state formulas in a natural way. What's interesting is that all programming constructs are definable in this algebra. How do we do quantification? Well, there are operations of anti-domain. Anti-domain is implicitly universally quantified over choice functions. Essentially, it says there is no choice function witnessing a successful execution of T. There is no such a choice function. And the domain is existential. There is a choice function that witnesses the execution of T. These quantifiers can alternate, and because of that, we can formalize problems at any level of the polynomial time hierarchy. Let us talk about the main computational task here. We are given a relational structure and a term. And the question asks, using this modality, whether there is a successful execution of that program starting from that input. This is an input state. Is there a successful execution of that? And the successful execution is witnessed by this function. For example, we can describe circularability in a term like that, OST reachability. H will be a witness or a certificate. Then a computational problem specified by an algebraic term is an isomorphism closed class of structures such that this condition is satisfied. And we can view it as a game, whereas the arena is a transition system, and given a term and a structure, whether we can have a successful strategy, winning strategy, where we can reach the accepting state. Some examples. This is counting. We are given a structure on the input with an empty vocabulary, and the question is the size of the domain equal to 4? What we do is we guess a new element 4 times. It's just an abbreviation. This, the same expression is repeated 4 times until it's no longer possible to guess a new element. Guessing is formalized using the choice operator, essentially from the active domain from all elements. We pick one element, put it in P, but the choice operator tells us pick this particular element. And we also have a copy operation that is, we can copy from P to Q. Choice is not essential here. How do we guess a new element? We guess an element and look backwards in the computation. Then the content of P now is different from anything before in Q. And remember, P is copied to Q. So these two tell us that what we guess is really a new thing. And then the main task, the answer to the main question is true if and only if the input domain is of size 4. Similarly, we can formalize other counting problems, such as even, the query even, which is not in monadic second-order logic. We can formalize many reachability questions. I have one on the next slide. Briefly, I mentioned ST connectivity. We are given a graph and 2 nodes we want to reach, find if there is a path between them. We repeat, we repeatedly guess a new element which is reachable until no longer possible to reach. No, sorry, until we reach actually reach T. Also, examples with mixed propagations are possible, such as Gaussian elimination. Then also, we've done some NP-complete problems, but there is no time to look at them. The main theorem here is about capturing a complexity class. Well, essentially, the corollary of the two statements I have tells us that under certain conditions, we can capture the complexity class NP. What are the conditions? Well, the conditions are that negation is applied to atomic expressions only or to equalities. All choice functions are of polynomial lengths. That is, after a polynomial number of steps in the size of the input structure, the choice function says, sorry, I'm undefined after that. Then the first theorem says that the data complexity of checking the main question is in the complexity class NP under those restrictions. The proof uses structural operational semantics. We guess a choice function and then apply the rules of structural operational semantics, which I don't have time to go over. But we return yes in polynomial time if H is the witness, and we return no in polynomial time otherwise. The second theorem shows that every NP-recognizable class of structures, for every such class, there is a sentence in the restricted fragment whose models are exactly in P, in K. And there we model a Turing machine. We guess an order first. We guess an order as in the examples we saw, as in the example for counting, we guess elements one by one, and we associate them with elements of a secondary domain. Secondary domain can be ordered. And then given that order, we run the computation. And this is purely deterministic computation after that. The structures on the input are not ordered. And as a corollary, we show it from the two theorems, we see that the restricted fragment of the logic captures the complexity class NP. In general, because of the alternation of the quantifiers, we can represent problems at any level of the polynomial time hierarchy. To summarize, I presented a logic in algebra on strings of relational structures. Operations are function preserving, can specify reachability, cardinality, and mixed propagations type of examples. A fragment of the logic captures exactly NP. In general, anything in polynomial time hierarchy can be expressed. And I believe that this is the first algebraic approach to capturing complexity classes. Now, open problems. Of course, the main interesting question is, under what conditions on the algebraic terms a naive winning strategy is possible? What is a naive strategy? Well, at each step, we simply make any possible choice, and we are guaranteed to succeed. Going back to the quote, all the time life is a fork. If you are straight up with yourself, you don't have to decide which road to take. Your karma will look after that. So this question is about karma. Well, in fact, this is a nice mathematical question. It is hard. And I know the conditions for a few years already. So hopefully something will be done, put in the archives soon. Okay, other questions is to connect to other logics, algebra and automata. Very interesting whether the modal substitution calculus is related. I think it is. Then there is a proof system we're working on with some colleagues. And it's interesting to connect, that is not done yet, but it's interesting to connect to existence of a proof as a certificate with the existence of a choice function. And it's interesting whether interpolation theorem holds, for example, for a fragment. And that concludes my talk. Thank you. Thank you very much.
I have a beautiful title for a theorem. You just need to fill in the detail. The karma theorem. Now go and figure out what is your karma theorem. Okay. Let's save all questions to the speaker for the afternoon. We are late for lunch. See you here at 2 o'clock.